Perfect. Thank you very much for letting me know, guys. It's obviously put me on mute. So as I was saying, welcome to part 3 of this webinar series. Welcome back for those that have previously attended one of the 2 webinars, or if it's the first one you are attending, a very warm welcome. Bit of introduction. My name is Rob Green. I am the Hydronic College Training Manager based in the UK, and part of my responsibilities include the ANZ markets. So this is now the 3rd session of what will be 6 webinar sessions we are conducting over a few month period. Let's just see how many we have online. I can see this person, check. I can see we've got nearly 25 people online. So I think we're 2 minutes past the hour. So I think we can make a start. So I want to make a start, as I always do. Bit of an introduction, some basic housekeeping for today's webinar. We will be recording the webinar, and everybody that's attended will get an email shootout sometime later this week with an access to that recording. Just so you know, your mics and cameras will be disabled, and there will be a slide pack in PDF available for all attendees, again, that will come out as part of that introductory email with access to the recording as well. If you have any questions during the webinar, please find yourself towards the Q&A section on the Teams dashboard, and there you can create a post. And what we'll do is I will try to leave 10 or 15 minutes towards the end of this webinar so that we can answer any of those questions towards the end. And what I'll also do, I'll open up the microphones and cameras at the end of the webinar so that you have an idea to ask the question then. But if something pops up while I'm speaking, please just put it in the Q&A panel, and we will do our best to answer that at the end. So without further ado, let's have a look at the agenda for today. So today we're going to be talking about dynamic balancing. I'm going to start with a little bit of a recap over some of the items we covered in the first 2 webinar series, and then we'll delve into some of the new material we have for this part 3. And first thing we're going to look at is load changes in system and how that can actually affect the differential pressure throughout the system, and how that's actually going to affect what we're going to be doing with dynamic balancing. We are then going to introduce the differential pressure control valve, the DPCV, have a look at how those work, where we might to install them, how they operate. And then after that, we're going to look at pressure independent balancing control valves, or PIBCVs for short. And then finally, I'm going to have a little bit of a few slides around optimizing the variable speed pump when you are using dynamic balancing, which for me is probably the most important part of this webinar, because actually, as we'll learn during this webinar, if you've not used to these products already, they do a lot of the hard work for us. But if we can remember, going back to our recap, what is the purpose of balancing? And that purpose is adjusting the design flow to all of my terminal units to design conditions. And again, today we are still going to be talking about design conditions only, i.e. when we are at full load of the system and all control valves are open. And the key part, which is what I said for me is one of the most important things with this, is while we create the minimum of additional pressure drops. And we learned last month about some methods that we could use to balance when we were talking about manual balancing. And we're coming at the webinar today with the idea we have already, if we're using partially manual balancing, we have already manually balanced the system. We've already set that system, parts of that system to design conditions, and the use of the differential pressure control valves is going to be to split that into different areas. So the most important thing, or one of the most important things when we talked about balancing, was the module itself. So we're talking about a direct return piping system, piping network. So we are directly flowing in and directly returning back on this network. And the other thing we talked about was the proportional rule. And again, we're going to use the proportional rule as a great asset once more when we're looking at the differential pressure controller and dynamic balancing. And the proportional rule is applying itself that when we make a change, downstream of that change, everything is impacted in proportion. And that same impact applies itself if I was to make a global change here to the total flow in this single module. The change I made here would affect all of these units in the same proportion. And that is what we're going to be leveraging a lot when we talk about the dynamic balancing side of things. Another important topic we covered in the first week was looking at how we split systems into modules. And once again, we want to imagine ourselves when we're splitting it into a module. In particular with DPCVs, differential pressure control, it's really imperative we follow this same module structure because we need to ensure all areas of my system are created with using some form of differential pressure control. And I often use the word protected by a form of differential pressure controller. And we saw with those that we could break systems down to have a main module in this example here. This is a single floor where we have one floor main module. And in this example, we have 3 submodules off there, and then a number of terminal units, either part of the main module or being submodules off those subs. And again, when we look at DPCVs later, we're going to be looking at splitting into modules is one of the most important rules when we're looking at the design of a system using DPCVs. And then last month, we were talking about some different methods, and we investigated the TA wireless and TA diagnostic manual balancing methods. And we saw some of their advantages, and we had a couple of case studies showing how we can really leverage a good design. And the key thing being, and we're going to come back to this, is ensuring when we are manually balancing system or balancing in general, that we're doing so whilst introducing the absolute minimum of pressure drops to ensure we are optimizing the running of our pumps. So that a very short recap of what we covered in the sort of 2 hours or so previously. We're now going to look at load changes. So load changes, what do I mean by load change? In the previous modules, we have talked about a static system, setting it up to a fixed point where nothing changes. And actually, when we bring in dynamic balancing, the reason for the invention and proliferation around dynamic balancing valves is not necessarily for the balancing aspect, it's for the in-use aspect. And if we take a typical system, typically a system will operate at around half a load or below for a very considerable fraction of the cooling or heating season. So you can find that you may be running somewhere like I think in Melbourne, you can run for a very considerable amount of your time, nowhere near maybe 50% up if you've designed a cooling system for, say, I don't know, 1 megawatt worth of cooling. You're going to be spending a large proportion of that season at a lower requirement because the outside temperature is not going to be that design outside temperature. It's going to be a lower temperature. So you're going to be gaining less heat into the building. You're going to need to provide less cooling to compensate for that. And we always talk about calculating for nominal conditions at maximum load. And if we move that into a to coming back to look at flow and differential pressure, if I take a 50% of load, so we said a large proportion could be, say, up to 80% of my heating system, that represents in a normal, say, 6, 12, 24, so 6 degree supply, 12 degree return, 24 degree target room temperature, that will account for somewhere in the region of 20% of design flow. And we look at our famous inverse square law that we introduced in the first week, where the differential pressure is proportional to the square of the flow, i.e., if we have twice the amount of flow, we have 4 times the amount of differential pressure. And conversely now, if we only have 20% of the flow, we only have 4% of the pressure drops in the system. So if we imagine a manually balanced system where we had set a static point and we'd set every valve in the system to remove an amount of differential pressure, there is only going to be, for 80% of the year, 4% of those pressure drops throughout the system. So what that means in general is that the pump head, if we're running a constant head pump, is going to apply itself almost entirely on the two-way automatic control valves. And in the next couple of series after this, we're going to be looking at control circuits. But for today, we're going to be looking at the balancing side of things. But I wanted to introduce why these differential pressure controllers are there, why they started to become around. And it was because of two-way variable volume systems, where we were spending 80% of the time, may only have had 4% of our design pressure drops. And you could say, well, yeah, that's fine. Well, if we've only got 4% of the pressure drops, why don't we just turn the pump down? We have a variable speed pump. We can lower that pump speed and produce less pump head. So therefore, it's no longer an issue. We have our balance back. But if we look at a typical system, so this is an example system where we've got 1, 2, 3, 4 risers with 4 units off each. So fairly small system containing 16 units. If we took a 100 kilopascal design pump head at maximum flow, we were saying we were going to be losing 65 kilopascals in the piping, 15 kilopascals in the two-way valve, and 20 kilopascals in the circuit. At low load conditions, for the sake of ease, we could say that 65 kilopascals is no longer taken out at all. So in essence, we have an excess of 65 kilopascals in the valves. So that's going to mean, if nothing else changes, we've got a large increase. In this case, it's over a 4-fold increase, nearly 5-fold increase in differential pressure, which is going to lead to an increase in flow through that valve. So we're going to no longer have a balance in the system. We're no longer going to be able to maintain conditions, and we're not going to be comfortable. We're going to get potential noise in the system. Control valves not being able to shut off, too higher flows, differential temperatures being impacted. And you could say, yeah, well, that's okay, Rob. I've got a variable speed pump. I can simply tune 65 kilopascals off that pump. But what happens if actually this system here still requires full flow? Dropping this pump speed right down is going to mean we're going to starve this valve here, and we're not going to be able to have system comfort again. So we're going to need to look at a different way of doing things. And the variable speed pump is not compensating for all of this. So we may need to look at something different. And this is where the differential pressure control valve, the DPCV, may come in. So for those of you that may not be familiar with a differential pressure control valve, I thought I'd do a very quick recap on what they are. So the DPCV, the differential pressure control valve, is a device that is able to maintain a stable differential pressure between 2 points. And we'll go forward a slide in a moment to have a look at what those 2 points would be. And it is able to react dynamically to changes in differential pressure. So you can see in this graphic here, we're seeing a dynamic changes in available differential pressure externally to the DPCV. And the DPCV is providing a nice quasi-constant differential pressure within the circuit or device it is installed upon. So that is the essence of the valve. It is providing a stable differential pressure under varying available by opening and closing. Typically, they're going to be comprised of 3 main components: a diaphragm, a seat for the control, and a spring to provide an external force to act upon. So let's have a look at an example with our STAP, our STAP valve. Here we have a circuit, and in this example, the pressure we are controlling, the 2 points we're controlling between, is the inlet pressure here and the outlet pressure of the outlet static pressure. So the difference in pressure between my P1, my incoming available pressure, and my P2, my downstream pressure of the circuit. And this is the pressure we are wanting to maintain in a stable environment. And we can see a few of the components within the DPCV here. We've chosen the STAP here because it represents fairly simply a differential pressure control valve in action. And here we have my diaphragm, one of the most, if not the most important component of a differential pressure control valve. And this diaphragm here is separating my high pressure, my P1, and my low pressure P2, i.e. my differential pressure across the circuit. So if P1 increases, that's going to add a higher force to for the top of the diaphragm, so it's going to move my plug down. If P2 increases, we're going to get the opposite. And then this is my plug that is going to be when my diaphragm is moving up and down. We're going to be opening and closing this plug to dynamically change how much differential pressure this STAP or DPCV is removing from the system. And finally, so last but not least, we have my spring. And my spring here, in the case of a DPCV, is on an adjustable platform, so I can adjust that spring force. And what that spring is actually doing is it's actually physically pulling that spring and that seat and diaphragm open. So we are providing a force to open the valve, and an external force is being provided via pressure P1 and P2. So we can see the difference between P1 and P2. When that is equal to the spring force, my valve will sit in position. When it's different, if P1 is higher, it's going to close. If P2 becomes higher, i.e. my differential pressure is less, it's going to open. So let's look at an example. So first of all, we have my pump is off. My system is full, vented, and we're going to say we've already balanced downstream of my circuit. This circuit has already been manually balanced. So we're now going to look at adjusting and setting and seeing an operation. So it's now just installed, nothing's running. And we're going to also say we've now vented my differential pressure controller valve. So we've now vented all of the air out of here. So this is all full of water. My capillary is full of water, and we're ready to turn my system on. So we now turn my pump on. In this example, I've turned my pump on, but my pump is not at full speed. We now have an available head into the circuit of 20 kilopascals. And at this point, with no adjustment on the STAP, we have a 10 kilopascal pressure drop across. So we're maintaining a 10 kilopascal pressure drop across my circuit. So that's going to mean my DPCV is taking out the difference between the available head of 20 and the set point of 10. If I was to increase my pump head, we can see, we'll play that again, you can see we get a slight movement of the seat. So we now maintain again a stable differential pressure of 10 kilopascals, and my DPCV is reacting to take out the difference once more. So that DPCV is closed. So with nothing, no else changes, my flow is the same through the circuit. So therefore, this differential pressure controller has to be more closed to take out that additional differential pressure. And again, if we increase it further, it's going to close further. And it's going to continually run around here to maintain a stable differential pressure between my P1 and P2. So P2 is seen on the bottom of the diaphragm through the internals of the valve, and P1 is provided from this high pressure capillary connection. So now let's say, right, we don't want 10 kilopascals. We've now turned my pump on. My pump is running at full speed. The available head in my circuit is 60 kilopascals. And let's say we were not measuring the correct amount of flow in this circuit. So if you remember from week 1, we talked about my differential pressure is proportional to the square of the flow. So to increase the flow through this circuit, we must increase the available differential pressure across it. And we can do that via adjusting the STAP. So in the STAP, in the example, maybe other ways of doing it, you have an Allen key slot for the example of this. And when you turn the Allen key, what you're actually doing is you're moving this spring pedestal here. You're compressing the spring, so increasing the spring force. And by increasing the spring force, that means you are effectively opening the valve further and providing a higher differential pressure across the circuit. So as we increase the spring, we're going to turn my Allen key and we're going to increase my differential pressure across my circuit. And we can see as we are moving this down, it is adjusting that, and that's how meeting my desired level. So it's moving up and down to provide there. And we're going to say, right, we've adjusted it. DPL is adjusted to the correct level of 30 kilopascals. And we can now say my DPCV is controlling. So now if we get an increase in pump head once more, because something else has happened in the system, my DPCV is going to react to that, and it's going to provide a stable differential pressure. And you'll note that it's not entirely stable. It is increasing slightly. And that's because of what we call the proportional working range of the spring and DPCV. A DPCV is by its nature a proportional controller. And for any of you who have done anything with control, you will know that proportional control means it has to see an error. So we must see an error to act upon it. So if there's no error, the valve can't act. So there is also always a proportional working band. Depending on the design of the valve, it can be anywhere from about plus or minus 20% of differential pressure up to about plus or minus 50 or 60%, depending on the type and design of the valve. But in essence, for the sake of it, we're only getting, in this example, 10-ish% difference maximum under an increasing differential pressure. And this valve is shutting down to take out these differences and maintain a quasi-static differential pressure in the circuit. And that is the essence of how a DPCV operates. It's continually opening and closing as my differential pressure is changing to maintain that stabilized differential pressure downstream. By virtue of that, my DPCV is continually having a difference in differential pressure across itself, because it's taking out that difference between what the circuit needs and what the available is, as long as we stay within the working range of that valve. So that is a very short overview on the inner workings of DPCVs based around the stat valve. And we can see it is dynamic in its nature. This is why we're classifying it as a dynamic balancing device, because when we're making changes, now we could be talking, these changes could be because we are commissioning parts of the system, opening different areas, extending the system, whatever it might be, and it is dynamically adjusting once we've set it to be able to achieve this. So we can see it's really, really important that we correctly set this design differential pressure, and we correctly commission the DPCV by adjusting its set point. So that's the operation. Let's have a look at some of the solutions we can look at. So what's going to be the best DPCV solution for your project? Now, that is a little bit of a loaded question because it's very much going to depend on many factors. But again, let's have a look at a system here. This is an example multi-floor system, bit of a strange layout with multiple branches, multiple areas. So what's the best DP solution here? Again, the very first thing we want to do is decompose this into modules. And here we can say we've got one main module running down the riser with a number, in this case, 1, 2, 3, 4, 5, 6 submodules, and then a number of subs. And then in fact, on these modules, we even have sub-modules off here. So the very first thing we want to do is break in and decompose it down into modules. And the thing we need to bear in mind and be aware of with DPCVs is we must ensure, if we are providing dynamic balancing, differential pressure control solutions into a building, into a project, every single part of that system must be protected. If you say, well, yeah, do you know what? I only care, this unit is the one I really care about being correct. So I'm going to put a DPCV on there because we can't have any variations in differential pressure and flow on that unit because it's imperative that it always operates. But we leave everything else open. That's not going to necessarily solve the issues you have here, because water's fundamentally lazy. If it's got to do more work to get through the DPCV here, it's going to short circuit that and go to other areas of the system. So let's have a look, and let's start with the minimum amount. So we could, for example, look at placing a DPCV on the main control pipes, on the main piping. So we place one here on this main branch that is serving and protecting this branch here. So everything within this branch is now under a differential pressure control module. And we can say, yeah, we've satisfied the condition that this guy here is okay. But we must also then provide a DPCV here to serve all of these down here. Now that's pretty wide arching. We are providing a stabilized differential pressure across quite a large area. So that may not be enough, depending on, and we'll talk about things like valve authority, control characteristic in 2 sessions time, but there may be other options. Other options, we could look at, again, standard DPCVs on the sub-branches. So now each sub-branch is containing a differential pressure control valve. And again, we could say we're only interested here, but if we placed one here, we would need to place one on every other sub-branch. And all of these would be required to be set up and commissioned correctly. But the beauty is, if I was to set this one up, when I do any adjustments here, or here, or here, they will dynamically self-adjust and maintain their set point so long as there is sufficient available head and volume to satisfy the complete circuit. Or we could go right to the almost extremes, as it were, and we could place a differential pressure control on each terminal. Now, typically, I've just realized there is a item missing from my slide, so bear with me 2 seconds. These yellow parts are representing now DP control on each terminal, and the most common way of offering that in the modern world is with the pressure independent control valve. So now each and every terminal is going to have a dynamic device in a pressure independent control valve to provide balancing and control under varying available differential pressure. So that is the sort of the different solutions we could offer. And effectively, the closer we get to the terminal, the higher my authority is, the better my control is likely to be. But that's going to come on a commercial side. We're going to be more expensive. We're purchasing more DPCVs, more expensive solutions. So it's not always going to be the ideal commercial solution. And actually, we can offer lots of different solutions, myriad of solutions. In the final session of this webinar, we're going to be looking at our HiSelect software, where we can actually very easily compare different offerings and solutions with a few clicks of a button. So, talking of pressure independent control valves, let's introduce the pressure independent control valve itself. The PIBCV, pressure independent balancing and control valve. What it is a 2-way control valve, which is also combining a differential pressure and a balancing plug. Now, often the balancing plug and control plug are one and the same, but we need to differentiate that it is able to both balance and control, i.e. with a differential pressure, with a pressure independent control valve, you still need to set it up. You can't just fit and forget. It has to be set to the correct design flow. The difference here, the main difference, is the spring within the device is not adjustable. We will set the design flow by setting the opening of that valve. And my DPCV within the PIBCV, so in this example, this is our small modulator, this is the DPCV element here. This is it on the larger variant, and on the flanged variant, it is here. So this is the part that is providing a constant differential pressure across my control and balancing plug. And again, it's going to provide a dynamic reaction to any changes in available differential pressure or set point. And most importantly, preserve a high valve authority. And we're going to talk about that in a couple of webinars time about valve authority in a lot of detail. And we're going to look at and think about why that matters and how that's going to impact my system functionality. So let's have a look at a PIBCV in a bit more detail. This is our small pressure independent control valve. This is our TA modulator, a cut through example. And we can see here again, we have those same P1, P2 and P3 pressures here. Now the key difference is that the pressure between, it is now the pressure in this example between P2 and P3 that is remaining constant. So we have a P2, a high pressure, acting to close the differential pressure controller, and a P3 acting to open it. So as the pressure drop increases in P1, it's going to dynamically adjust. And let's see how that happens in action. And for me, I'm a visual learner. It's a lot easier for me to see it when we see it in action. So we have here, this side here, the left-hand side of your screen is the inlet for the valve. And this white section in the middle is the differential pressure controller itself. And what it's doing, it is providing a constant differential pressure by way of this spring force between the inlet and outlet side of the balancing and control plug. And you can see we have this internal capillary here acting to the bottom of the diaphragm, and internally the pressure is transmitted to this plug. So we can see when the pressure increases here, it's going to compress that plug. So we can see as we have changes, an increase in differential pressure, the valve's going to close. As it decreases, it's going to open. And we are going to dynamically, or the valve itself is going to dynamically adjust to any changes in available differential pressure within the working range of that valve during its operation. So this is assuming the valve has been set to the correct balancing set point to achieve the flow we require. Also, how we set a flow rate is pretty straightforward on these valves. Simply, we have to turn the setting wheel, if we're setting manually, to a desired value. So we will look in our valve charts and we'll say, okay, for a flow of, I don't know, 0.2 litres a second, the setting needs to be 5, for example. We put our valve to setting 5, and as you can see, that reduces the opening, and the DP controller is going to self-adjust to reduce its opening, because if we reduce the opening here, we're going to try to reduce the flow. So therefore, to maintain the same differential pressure across here, we're going to need to shut this section here to shuffle that differential pressure back across there. And it's going to be doing that as we adjust the setting. So very, very easy to set. To balance a system with pressure independent control valves is extremely simple when they operate as they should. Is simply we just turn and set that valve to control setting, and it will take everything away and do it all for us. The final section I want to look at is not so much for here, but a bit of a consideration, is actually a pressure independent control valve is via its nature a control valve. So that differential pressure controller is also acting when my actuator is closing and opening that valve. My DP controller is self-adjusting to provide that stable differential pressure and high authority across the control valve. So that is, in a short form, the operation of the differential pressure controller and the pressure independent control valve. The last section I want to look at now is looking at how would we optimize pumps with these systems. Now, with a manual balancing system, relatively speaking, pump optimization is a fairly easy procedure, because what we should end up with in a correctly manually balanced system is all, as we learned last session, is all of my differential pressure is contained in one valve. So simply, we just need to measure the differential pressure that's in that valve, reduce the pump head accordingly, open it back up, and everything should be absolutely perfect. It's a little bit different with a dynamic valve, because dynamically they are adjusting to change the differential pressure. So we need to make sure we are correctly adjusting, because these are dynamic products. They're made for absorbing excess pressure, stabilizing pressure, improving controllability. Variable speed pumps are also dynamic products made to adapting pump head to an actual load need, reducing operational costs. But often they're oversized. Very frequently pumps are oversized, because what tends to happen is we design a system and we say, okay, we need 100 kilopascals of pump head. We put 10 kilopascal, we put 10% on it for safety. Probably during that 100 kilopascal calculation, there's probably also 10% safety. So we're now running 10% safety on 10% safety. We go to a pump manufacturer and say, okay, Mr. Velo, Mr. Grundfos, Mr. Lawara, whatever, can you provide me a pump that will do me 5 litres a second at 110 kilopascals? And they say, okay, Rob, yes, here's my selection. And again, they're going to probably select the pump that's able to maybe deliver 120 kilopascals, maybe more. Again, it's oversized. So the key thing is, these pumps are variable speed. We can adjust the speed. We can adjust their set points. So how do we adjust that set point? What is the process we need to use? And again, it all comes down to balancing. And we're going to look at it with, in this example, DPCVs. But the process with a PIBCV is almost exactly the same. In fact, it's exactly the same. It's just the actions that are slightly different on where it's doing it. So step number 1. We must balance all of our hydronic modules, as we've already learned how to do with my usual methods. TA wireless, TA diagnostic, compensated method, whatever you want to use. My recommendation is always going to be TA wireless or TA diagnostic, but it's again entirely down to the engineers on site. That's going to mean all of my manual balancing valves are adjusted to take out the absolute minimum pressure drop they need to do to obtain design conditions. We then set each of my DPCVs to obtain the required total flow in the circuit, generally on the standard that's preset for 3 kilopascals. And as we adjust these DPCVs, we don't need to go back and visit the other ones because they were going to dynamically, as I adjust this one, that's going to dynamically change the differential pressure here, but this valve is going to react and compensate for those changes. So that's the beauty of dynamic devices. If this was all pressure independent control valves, once I'd all set them to set point, they're going to dynamically adjust to maintain 100% of design flow. But as the balancing procedure starts, my variable speed pumps are set at maximum speed when we're balancing. So at this point, we haven't completely balanced my system because a balance is only complete once we have optimized and set that pump to the minimum speed we need to do. And we want to take this quite methodically. So we need to set that variable speed pump. How do we do it? Clearly, we need to balance first. First and foremost, we must balance our system, enable the system to be able to achieve design flow in all areas. And this example here, we've got a system again with 16 valves in it, 20 valves in it, 4 modules of 5 terminals each. And we have manually balanced the system and set it to achieve round about 100% in all areas. 103% of design. And this is with my variable speed pump running at maximum speed. So at the moment, this is a simulator, so we have the beauty of seeing what the differential pressure and set point is of all of my differential pressure devices. And in fact, what I'm going to do now, I'm going to switch to a different screen. So I'm going to show you this live. In fact, let me close this because it's going to be a bit confusing. So we have my system here. And in this example, we're going to be setting it, and we've adjusted all of my DPCVs. So in fact, let's take them right back down a bit. Let's say they were there. Something like this. And we've now adjusted all my DPCVs to obtain 100% in each of my circuits. And you can see as I adjust here, dynamically, these valves are adjusting to maintain a stable differential pressure throughout the system. So you could say, yeah, fantastic. I have achieved design conditions. I could walk away at this point. But what I have not done is I haven't optimized my system. So the first thing I want to do is I want to now force now this may seem a bit backwards, but I want to force my pump to the minimum speed. So we're going to now drop it, and we're going to say we're going to drop all the way to, let's go all the way down to, I don't know, 70 kilopascals. Let's say that was the minimum speed of that pump. So we now set my pump at minimum speed. And as you would expect, at minimum speed of the pump, we no longer have a balance correctly in the system. And you can see that actually these first two differential pressure controllers are 100% open. Now, you wouldn't see that in a real system, but the beauty of having a simulator is we can show it. So these two valves are 100% open, and we can see we are only at 74% of design in this most remote circuit, 83% here, 90% here, and 90% here. So these two are slightly controlling, and these two are doing no control because there isn't enough available head. But we don't have the option in a real system of being able to see really what's happening here. So what we're going to do is we're going to have it doesn't show it here, we'd have a main manual balancing valve here where we're measuring that flow. And we're now going to increase the pump head in steps. So let's try, I don't know, 5 kilopascals at a time. Okay, we're now 87%. We're going to increase it to 85%. Okay, we're getting there. We can now see it at 91%. And again, these valves are dynamically adjusting. In the case of these two, they're not because they're not open enough yet. We're going to keep increasing my pump head to 94%. %. Keep going until we get to 100%. We want 100%. That's the aim. Don't think we're going to quite get there because the adjustments we've made. We'll keep it at 125. 99% is good enough for me. And you can see now, we now have between 99 and 100%. We've now back into a balanced scenario. And again, my DPCVs have self-adjusted, dynamically adjusted themselves to what they need to maintain everything at design conditions. And in this example, we've taken 25 kilopascals off a 150 kilopascal pump head. So we've reduced that pump head fairly by around 15% or so. Give or take 15-20% reduction in pumping head. And that's a direct reduction in OPEX there. So we can now say we've optimized the setting of that pump, and we've now absorbed all of the excess differential pressure in these valves. And we can now say we are fully in control. At 100%, we've optimized those pumps. So it's a fairly simple procedure, but it's a vital procedure. And in my experience, it is a procedure that is not often carried out. For example, I remember a big project in, I think it was a hospital in Ireland where we were having issues around our valves. And when we measured the differential pressure at one of the extreme valves, it was up at around 2 or 3 bar, which meant we had an excess of like 1.5 to 2 bar pump head in the system because they hadn't optimized the pumps correctly. So that is the end of the presentation for today. Once again, thank you very much for attending. Next webinar is going to be in the new year on control loops. If I could ask if you could scan to give any feedback on today's session, and I will now go back into here and see if we have any Q&As at all. Let's see. Nothing here. Is there any Q&A? To load. No Q&As of yet, but what I will do is let me just allow people to unmute themselves, and if they wish, turn on their cameras. So hopefully now you should be able to unmute yourself, I think. If there is any further questions, I can see a few people are dropping out there. Just before we go, is there any questions at all? Okay, fantastic. If you do come up with anything in the meantime, please feel free to reach out. And I wish you all a fantastic Christmas break and holidays. I think it's going to be a lot nicer weather with you down in the southern hemisphere than it is for us up in the northern hemisphere. Bit cold and wet for us, but I hope you enjoy your extended breaks. And I will hopefully see you again in the new year when we're going to start moving to look at control. So once again, thank you very much for joining, and hopefully see you next time. Bye.